All right, so my name is Runar. I'm going to be talking about things that I don't normally talk about, things that make me uncomfortable. I'm going to be talking about how functional programming is terrible. Okay? Now, those who know me, you know that I'm a functional programming zealot and extremist, but I'm going to do kind of like a counterpoint to that here now. I'm going to talk about sort of the other side of things. Okay? But obviously this is hyperbole and it has a happy ending. So if you were worried about that, then you can rest easy. Okay. So first of all, let's talk about how do I skip to the next slide? There you go. So first, let's talk about what functional programming is. What do I mean when I say functional programming? So I don't mean a buzzwordy, fuzzy kind of thing, like, oh, I'm doing functional programming because I'm doing maps and filters. I mean, programming where your entire program is a single referentially transparent expression composed of other referentially transparent expressions. Okay? No side effects, no mutability, no global mutable state, and that kind of thing. You still do, I/O and that kind of thing, but you do them in a compositional way, like with the Scala Z stream library and that kind of thing. Okay? So everything purely functional. That's what I mean by functional programming. So but let's talk about the reasons why this can be terrible. So reason number one that functional programming is terrible in Scala is that it insists on tail call elimination. This is not optional. And Scala does not have this. So this is kind of a terrible requirement. So what are tail calls? Let's first get that out of the way. Tail calls are sort of the last thing that a function does, right? So here, the call b of v is in tail position because it's the last thing that this function foo does in the true branch of this if statement, right? There's nothing further to be done. After calling b of v, there's nothing further that foo needs to do. And conversely, c of v here is a call that is not in tail position. It's not a tail call because it still has to add 1 to the result. The result is, the effect of that is that theoretically at least, the compiler could figure out that foo has no further work to do after calling b, and then b, instead of returning to foo, could return to the caller of foo. And that elimination of stack frames is tail call elimination. Now Scala does some tail call elimination. It can eliminate self-recursive tail calls. So here's a recursive definition of a factorial function that is not tail recursive. And so, no tail calls here, we can't do anything. But we can refactor this to be tail recursive. So here we can actually see that the go function, this helper function, is calling itself as the last step. And so Scala will actually figure out that there's nothing else that go needs to do after it calls itself. And so it will actually compile this to a jump instead of a function call. And a jump is exactly what a while loop is compiled to. So this while loop version of the factorial function is exactly equivalent to the tail recursive function that we saw before. But Scala does nothing to help you with inter-method tail calls, with tail calls between methods. For example, where this foo function is calling this b function, and this is because of Java's call semantics. So Scala has made this design choice that Java's call semantics have to be emulated or have to be compatible with Scala's. And so when you call a method, it implements it as the bytecode, invoke function. And so Java's call semantics require that there is a stack frame for every function call. And that's a real problem for functional programming. Because functional programming, being terrible as it is, it insists on tail calls. Why is that? Why is this important for functional programming? Well, it's because in functional programming, you may want to compose a lot of functions together. And you want it to be completely transparent that when you have a function and it's composed of a lot of other functions, you want that to be transparent to the user. But it's not. Because when you take a list of functions like this, let's say you have here a list of 100,000 functions, and you compose them all together, and then you call the resulting function of type A to A, that is going to overflow the stack. it's going to just crash. And there's some point at which that list becomes one too long. And it's not consistent between, 999 functions and 1,000 functions. It's going to just overflow the stack at that sort of breaking point. And that's really terrible. The solution to this in languages like Scala that don't have tail call elimination is to use trampolines. And the way trampolines work is that you have a data structure that represents your computation. So instead of just making calls, you suspend the computation and you capture it in a data structure. And here's how that works. You have a data type like this. Here I'm calling it tailrec. It can be one of two things. It can either return a value, in which case it will be constructed as one of these return cases, where it will actually have a value of type A. Or it could be a suspension, where you have a function, a resumption function, that something that can call to sort of execute a single step of your computation. And the result of resume is another one of these tailrecs. So you can imagine that this is sort of like a list of resumptions, where you call one resumption and it gives you the next one. And then you call that and it gives you the next one. And so you can sort of step through the computation one step at a time in a tail recursive loop, right? Until you hit one of these return things. Okay? And that's going to be at the very end when the computation has finished. And so that gives you the ability to be tail recursive. So instead of returning a value that you get from a function call, you put the function call inside one of these suspensions and return that. And the way that we can use this in our composition here is we instead of composing, just saying like and then, instead of calling our functions directly, and this is much longer, and more sort of difficult to see. But so we start with sort of the base case is that we return the answer, right? And then sort of at each element, at each function in this list, we suspend before we call that function. And so at the end, we then pass A1 to the result, and that's going to give us a tailrec that we then call run on. And run is a tail recursive loop that's going to then walk over all of those suspends and is going to actually run the computation. Okay? And a tail recursive loop like that is called a trampoline, because we're constantly bouncing back and forth between this function here that we have compose all and the tail recursive loop, which is the run method. So this does not come for free. Trampolines have a definite memory overhead. There's a limited memory overhead because these suspensions are being generated lazily. You don't have all of them on your heap at the same time, but they have to be created. And so you have garbage overhead, and that means that it's a performance overhead. And it has a further performance overhead because you're constantly jumping back and forth between two methods. It's not necessarily a hotspot. So when just-in-time compilation kicks in, it can't necessarily figure out that you have a hot loop. All right? So this can have devastating performance implications. But function composition in Scala can't be done, basically, in any sort of large degree without trampolines. And monads can't be used. Like, they're basically useless without trampolines. Non-trampolined monads, if you have a chain of flat maps where you have something and then flat map and then there's a function that calls flat map again, and if you do that in a loop, that's going to overflow the stack. And there's no way around that except using trampolines. And that is terrible. So reason number 2 that functional programming is terrible is that it insists on higher-kinded types. Higher-kinded types allow you to do code reuse. And so to write sort of higher-order abstractions that, so you don't repeat yourself all the time, you need to have higher-kinded types. So, I mean, Heather talked about higher kinds, so I'm not going to talk too much about what that means. But so you can think of kinds as the types of types, right? So int has the simplest kind. It's of kind star, or it has no further sort of shape, doesn't have any content. And list of int is another sort of simple type, but list by itself is not a type, it's a type constructor. It needs a type to construct a type. So you have list, you give it a type of kind star like int, and it gives you another type of kind star, which is list of int. And then either is a binary type constructor, it takes 2 stars and gives you 1 star. And monad is a higher order type constructor. It takes a type constructor of kind star to star as its type argument and gives you a type of kind star. And now in Scala, this is annotated with these underscores and brackets. So if you have a higher kinded type like TC here, a higher order type constructor, you annotate it with these underscores and open brackets and more underscores. Okay? So what does this buy us? It buys us code reuse. We can write functions like this, like traverse and sequence, which are very general and extremely useful. So traverse is kind of like map, except that the function f is not from a to b, it's from a to g of b, okay? Where g is some applicative functor, okay? And what that means in practice is that whatever g may be, it could be option, or it could be future, or something else. What it means in practice is that you sort of map over this list with this function f producing a bunch of futures, and then this function will then take all of those futures and combine them into one future that runs all of those other futures in parallel and gives you a list of the results. So you can see that the result type of traverse is g of list of b. So a simple sort of derivative combinator that you can write is sequence, where if you have, say, a list of futures, it can give you a future of a list of all of the answers of those futures. If you have a list of options, it can give you an option that's none if any of the input options are none, or sum of all the answers if all of them are sum. Okay? Importantly, you have to write this only once, because you can abstract over the type constructor and over the applicative functor g, and you can take that type constructor, so you can say sequence and traverse have higher kinded types. So you write this once and for all. So applicative functors are things like future, list, option, and it's useful for all of those things. But there's one of these things is not like the other, right? State here, which I think somebody talked about before. State is a way of sort of purely functionally representing a stateful computation. It's just a function. It takes an input state and it produces an output state together with a value that's computed from that state. And mapping over this and flat mapping over this is just function composition. Okay? But if you wanted to use this with traverse, you can't do that because Scala lacks this higher order unification that Lars was talking about. So what happens is that because state has a different kind of different shape, a different kind than option, list, and future, Scala will not be able to figure out that this is OK to do, that I can actually use the state applicative functor here and write this. So it's actually going to tell me that there are no type parameters for method traverse that exist so that it can be applied to the arguments that I gave it. And that is a blatant lie. And I can prove that because all I have to do is just tell it, hey, there is a type constructor, I'm going to call it lambda, that has the right kind. It takes a single type argument x, and it is equal to state of int and x, and then this is all going to work just fine. But I have to do this now everywhere I call traverse with anything that I want to sort of like partially apply. That doesn't fit into this neat picture of type constructors with a single type argument. Now, if Scala, we can imagine a Scala that had this feature of type currying, where instead of having, or we could have in addition to having state that takes 2 type arguments of kind star, we could have a state that has 2 type argument lists, very much like we have curried functions at the value level. So we could have a state that takes a type argument of kind star, which then returns a type constructor that takes the other one. Okay? And then we could just partially apply state with int, and that would have the correct shape, the correct kind to be used as an applicative, and then everything would just work. But it doesn't. So we need to resort to violence like unapply. So this unapply thing lets you say, if you have an implicit instance of this unapply thing, it lets you say that, if I want to traverse a list with a function from A to some other type g of B, I take implicit evidence that there exists some type constructor M that is an applicative functor, and g of B can be deconstructed into M and A, so a type constructor M and a value A, where GB is equal to the type M of A. Okay? And this is really kind of painful to look at, but again, Scala-Z and Shapeless do this boilerplate work so that you don't have to. But you do have to write your own traverse instances if you want to write your own type constructors. Okay, so when we've written that traverse U, which was written in terms of traverse, we can now pass it a state action and everything will be hunky-dory. So kinds in Scala are really sort of insufficient for our purposes here. It's really kind of terrible that we have to do this work at all. So kinds are never inferred. You always have to supply kind annotations. So you can't say, I have some type, something M, and it may be a type constructor. I don't know. Scala, you go figure it out. It can't do that. You have to always annotate. And not only do you have to annotate them, you also have to annotate the kinds of the arguments to your type constructors. So when you have, when you annotate the kind as a type constructor, and that type constructor takes arguments, you have to annotate whether that type is a type constructor and what the kinds of the arguments to those type constructors are as well. So it really gets, and variance is part of the kind of any type. I didn't even mention that. So that's horrible. So how can we make functional programming less terrible? Well, some suggestions. We could have tail call elimination. That would be fantastic. But we don't have it. It would be nice to have kind inference, or a kind system at all. But for now, we just have to annotate everything with our kinds, and sort of use implicit evidence whenever we need to do anything complicated. We do type level computation. It would be great to have better type inference. Like just when you need type inference, just when you need to sort of tie the knot and say, OK, figure this out for me. I have a recursive function. Figure out what the type of this thing is. Nope, can't do it. It's a recursive function. You got to give it. Got to give me a type annotation. OK. And again, all of this has memory overhead. So whenever we do functional programming, we work with unboxed function reference. With boxed function references. So whenever you have a first-class function, it's actually an object. And that's really just a waste of memory. That doesn't need to happen. Sort of the general direction that we should be going towards is to minimize the runtime representation of our denotations, of our functional representations. Okay? It would be nice to have real existential types, but we don't have those. It would be great, if when I pattern match on something that has an existential type, I would get something other than a class cast and then a class cast exception at runtime. It would be awesome to have universal quantification, so we can talk about things like, parametric polymorphism and, rank 2 and rank n type functions, so that we can really make use of parametricity. And another thing that's kind of terrible is that you can have side effects everywhere. You can throw exceptions wherever you want. And Scala isn't going to tell you anything about whether that's going on. Okay? So whenever you call something, you can't be sure. You can't be sure that it's not going to, fire the missiles, right? So that's, that makes me depressed. So what is functional programming really for? Is it really just a hair shirt? Are we just putting this thing on because we want to be academics, and should we just throw this stuff out and just use global mutable state everywhere? Because that's going to be fast, and and whatever. And no, we should not, right? Because why? Why shouldn't we? Well, because the alternative is even more terrible. The alternative is, global mutable state. The alternative is remaining at the status quo. It's side effects and horribleness. Okay? The alternative to functional programming is unreasonable and incoherent code. Okay? So in truth, functional programming is actually a huge win, even with all these annoyances. And I would say compared to those wins, these annoyances are very, very minor, which is why I do functional programming in Scala at all. So reason number one that functional programming is awesome is modularity. Okay? Now, what's modularity? Modularity is the property that your software can be separated into its constituent parts, and those parts can be reused independently of the whole, and they can be reused in sort of novel ways. They can be reused in ways that you did not anticipate when you created those parts. All right? What does that buy you in practice? It buys you modularity. What does modularity buy you in practice? It buys you reusability, because obviously if you can take out the parts of your program and then you can reuse them sort of independently of the whole, obviously that's going to give you reusable code. It's going to give you testability, because if you could take your thing apart, you can pull out a part of your program, and it's not like going to have wires hanging off of it that you don't know what are, and then you can test that thing independently of everything else. It's always safe to test a purely functional component. And these things are parallelizable as well, because it's safe to separate things out and run them separately in a separate thread, if that makes sense. And you gain this property for the simple reason that functions are modular. And functions are modular because whenever you have an A and you want a B, and then you have a function of type A to B, it's always safe to just take your function of type A to B and put it there. Yeah? It always makes sense. There's nothing else that you need to worry about. It's always testable, because you can always take a function and you can test it. You can always, a function of type A to B, it's always safe to just give it its arguments and look at the result and see if the result is what you expect. It's eminently testable. And it's always safe to call a function from multiple threads, and the order of execution is not going to matter. Because no mutation is going to escape, and the pure function is just going to return a value. All right. Reason number two that functional programming is awesome is compositionality. Now, compositionality is the property that your software can be understood as a whole by understanding its parts and the rules governing the composition. All right? And what that means in practice is scalability, because large programs become exactly the same as small programs. They're going to be composed of some parts that can be individually understood, and the laws are going to ensure that as things get larger, they don't get more complex. You're going to just, if you have a function of type A to B, it doesn't matter if that function is composed of a trillion other functions. The interface remains exactly the same, and you reason about this thing exactly the same way. So compositional programs are reasonable, because at every level, you have pieces that can be individually understood by looking at their pieces and how they fit together. And so you get this property of compositionality by the simple fact that functions are compositional. If you have a function f of type A to B, you have a function g of type B to C, you can always put them together into a composite function of type A to C, and that is also just a function, and that could be composed of 100 other functions, and it can be used in compositions as well. Okay, so that gets me through the third reason that functional programming is awesome. And I think that this is something that we don't talk about enough. And we need to talk about this, right? Functional programming makes us happy, right? Because I'm being serious. I really think that, it's like, oh yeah, we're logical and we're programmers, so we gotta we got to not talk about our feelings, and we got to, you know, just get on with it. But no. Why? Why do we get on with it? Why are we here at all? Why do we program? Well, because programming is exhilarating. Programming is exciting. It's awesome. At least, you know, at first, when you start a new project, right? It's great. You know, you start a new project, you feel, you know, awesome, you're coding away. And then after a while, your project sort of, you lose control of it. It starts to feel, so yeah, I'm talking about my feelings. It starts to feel like a big mull of mud. It starts to feel like you're trudging through a swamp whenever you want to change anything. And it starts to feel, you know, like you have a sense of revulsion. Like you don't want to touch the code base because, you know, it might break, or, you know, it's going to be very difficult to get through. And so fixing bugs becomes, you know, difficult. You start to procrastinate. It's terrible. So reasons why functional programming implies happiness is that you have, you know, less of this friction and frustration. Because functional programs are modular, you can, you know, pull things out and you can move them around. So there's less of this friction that, you know, whenever you pull something out, it's going to be stuck to all kinds of other things. But you can always just, you know, take something out, maybe throw it away, replace it with something else. It makes things very sort of easy and pleasant. Things are more predictable. So functional programs, you know, they behave according to certain laws. And so if you make a mistake, you know, the laws will ensure that you know, that mistake is going to have some effect that is sort of bounded by something sensible. You know, it's not that if you make a mistake over here, then this thing way over here is going to break that has no seeming relation to that at all. So it really kind of constrains things. And you have less cognitive load because there are fewer things that you need to keep in your head. The only things you need to keep in your head are sort of the broad abstractions, and the implementation details kind of fade away. You know, and for myself, like whenever somebody asks me, like, oh, how does this, you know, this library that you wrote, like, how does it work, you know, under the hood? And I'm like, I don't know, it's a monad, you know? It's like, I don't have to know. I only have to know, I have to keep it in the back of my head, some abstract principles, some laws, and then when I come back to it, I know that it's going to make sense because, you know, I know that I wrote it according to those laws. I don't really know or care how I actually did it. Okay? And the solution space is smaller. So there are fewer programs that you can write. And that doesn't mean that, oh, you know, we're constrained and we're in a, you know, we're in a straitjacket and we can't, you know, do anything. It doesn't constrain what you can do, just how you can do it. You can think of it as roads, you know? Roads constrain you so that you don't, like, drive into the wilderness and get, you know, stuck in a rut, in a ditch or get killed or something. But they still allow you to go, you know, wherever you need to go. And so the search for the solution to a problem is really sort of constrained along a path, or it's sort of like a branching path, all right? And this makes finding the solution much more pleasant because you're much less likely to run into trouble. And this makes you more productive because you can find the solutions faster because the space is smaller. And lastly, it gives you pride because once you've built something, you can be sort of sure that it you know, that it conforms to what you were trying to accomplish. You know, it looks and feels clean. It is a solution that is reasonable, and you can hold it in your head and you can look at it and you can say, well, this is, you know, this makes sense. It's awesome. Okay, so I asked some people on Twitter, how does functional programming make you feel? And the response was overwhelmingly positive. So for example, Rob said, functional programming makes me happy because there's never any unstated context to have to know about. So it reduces his cognitive load. It makes him more relaxed. And yeah, Richard says, it makes me feel calm. I don't have to keep as much in my head to get stuff done. My favorite one is by Katie, where she says, functional programming makes me feel sane. I feel like a mathematician and an artist living in a beautiful, structurally sound, clean house. So I wish we would talk about, you know, our feelings more. you know? Because this stuff is great. It's inspiring. It makes me want to work. Because, you know, why are we here at the end of the day? I mean, we're not here to, you know, increase social utility or to, you know, increase the bottom line for the company. No, we're here because, you know, functional programming or programming in general is awesome, and functional programming sort of amplifies that. So, in summary, functional programming, yes, it can be awkward and terrible, but the alternative isn't possible, right? The alternative, you know, if I couldn't do any functional programming in Scala, I would not write a single line of Scala. I would just not do it because the benefits are just too great to pass up. And so we have to insist that our tools get better at this. We have to insist that Scala get better at this, or we have to just leave it behind. Because I really think the alternative is an impossibility. The alternative is, you know, the status quo. We have to be able to move forward, and I really think that compositional and modular software, you know, and being able to reason compositionally about software is the way to get us to, you know, programming sort of in the large. And this last point, I would just want to emphasize that your happiness matters, okay? Like, pay attention to what makes you happy. Like, don't resign yourself to just like working for the man and like doing the thing that's pragmatic or whatever. But, you know, pay attention to you know, what makes you happy as a programmer, because ultimately that's what life is all about. And like, happiness is how you experience what it's like to be alive. Thank you. So I don't think I have time for a couple questions if anybody has. Yeah. Can functional programming in Scala get better, and will it get better? From what I've heard today, yeah, it can. I think that, you know, it's software, right? You can do anything. It's never the end of the road. And so if you have something that is intractable and terrible, you can always just throw it away and you can start from scratch. I mean, you know, they're starting over with this Dotty language. They're starting from a calculus that is reasonable. And so, yeah, no, I think that I really don't know the answer, but it's certainly not outside the realm of possibility. Another question? Well, I mean, Haskell does have other problems, but yeah, I mean, I think Haskell generally has the things that I want. And yeah, you know, when I'm sort of programming on my own, I tend to choose Haskell just because like I don't have to deal with a lot of these things. But there are other things that I might need to deal with if I want to write. Whenever I need to write something that's you know, sort of for production or whatever, I tend to find that a lot of libraries don't exist yet, and so I might have to write them myself. So, but that's, you know, that's not a permanent problem, obviously. So we can always get better.
For something like that?
I don't have a vision for what that would look like. I think that ultimately either Java's call semantics have to get better, or you know, it has to supply a tail call bytecode or something. And failing that, we basically have to just implement our own runtime. And I mean, that's, you know, it's software. Well, there was a question over here. I'm going to take one more.
What are your thoughts on memory easier?
I don't know that that's true, that you can reason about memory easier. You certainly can't reason about memory usage compositionally. So if you start to you know, compose your programs of oh, I'm sorry, I've got to repeat the question. The question is, do you get better memory usage from, can you reason about memory usage easier with imperative programming than functional programming? I think the answer to that is no. Okay. That's all. That's all I'm going to say. Okay, thank you very much. I'm out of time.